Gracias.
Thank you. Our next speaker is going to be Professor Alfred U Ren from Instituto de Ciencias Nucleares UNAM in Mexico City. He's going to talk about exploitation of spatial...
No está funcionando. Okay, sorry about that.
That's okay. I understand. He's going to talk about exploitation of the spatial degree of freedom in photon Paris states. Thank you very much.
Okay, thank you very much for the presentation, and I would like to really thank Mauricio, Neil, and Karina for organizing such a great conference. So I will talk about some experiments that were carried out, some in my own lab and some in the lab that is run by Roberto Ramirez in Lyon. Okay, so I would like to just spend a minute to talk about quantum technologies in Mexico. So we have like 3 different organizations that I think have been very useful. So the first one is the Quantum Information Division within the Mexican Physical Society. And this was formed some time ago, like 12 years ago. And for example, we've had a yearly conference without exception since that time. Sometime later on, around I think 2015, CONACYT offered the possibility of what they called thematic networks. So what this meant was that we could have some additional funding for general purpose collaboration and so on. So we ran this network for a number of years until last year, this year, the new government decided to terminate this program. But anyway, these two have been very useful, and in general, they have benefited the whole community, I mean, both theorists and experimentalists. Also, there is the national lab, the Quantum Matter and Quantum Information National Laboratory, and this is another CONACYT program which has been running for some time, and it has been in charge of José Jauregui, who's here in the audience. I had the honor of presiding over the division, and also I coordinated this network until last year. Okay, so my talk outline, I will talk about, in general, about how to exploit the spatial degree of freedom in photon pair states. So I'll talk about 4 experiments. 2 of them have to do with quantum optical coherence tomography, and there's 2 different experiments in that area. I will talk about amplitude transfer in SPDC experiments, in particular with Bessel-Gauss beams, and I'll talk about direct imaging of OEM conservation in SPDC. Okay, so in general, in our laboratory, we have a number of sources. So we have, of course, spontaneous parametric time conversion. That's the one that we've been working on for the longest time. We also have experience with spontaneous Fourier mixing sources. So this is Chi2, this is Chi3. We've been trying to implement a source of photon triplets. This is based on a proposal that from our group from a few years ago, and there are a number of technical hurdles. We have a paper that we just submitted with like a progress report. This is with tapers, by the way, so there were a number of presentations using tapers, so this is one more use for tapers. So we haven't had success, and nobody else in the world has been able to show this, but we have made a bit of progress. And also we have now some sources which are also using tapers that are based on macrocavities. All right, so I will, in this talk, as I said, I will concentrate only on SPDC sources, and I will talk about 4 experiments, 2 of which were carried out in my own lab, and 2 of which were carried out in Roberto Ramirez's lab at CIO in Lyon. Okay, so for the purposes of the work that I will present here, the collaborators are the following people. So there's a lab technician, Hector Cruz, these 3 collaborators, Roberto Ramirez at CIO, Dorilian Lopez at Tec de Monterrey, José Jauregui from UNAM. There's these 3 PhD students, 2 of them have already graduated. One of them is at ICFO, one of them is at Heidelberg, one of them is close to graduating. A PhD student from CIO, and a number of master's and bachelor's students. Okay, so spontaneous parametric time conversion looks like this. These are cartoon representations. Basically, we have an energetic laser which illuminates a Chi2 crystal, and occasionally a photon from the pump will decay into, will be annihilated, and two photons will be created. If we put together all of these photon pairs, they will fall on the surface of a cone. For this type 1 case, which means that the two photons have the same polarization, and two different cones that may intersect in the case of type 2, which means that two photons have different polarizations, and of course momentum energy must be conserved. Okay, so because the first topic that I will cover is QOCT. So QOCT is based on the Hong-Mandel interference effect. So I'll just spend a little while talking about that. So this is a very well-known effect. We have photon pairs which meet at a beam splitter, and what happens is that there's destructive interference, and the two photons come out together, either through port 1 or through port 2. The two other possibilities do not occur when the two photons are indistinguishable. No, so if we introduce a delay between them, there is a null in coincidence counts for zero delay, and then the counts will go to some background outside of that. And this is an example from our lab. Okay, so quantum optical coherence tomography, it was proposed some time ago in these papers. And as I said, it's based on Hong-Mandel interference. So we have a crystal, a pump laser, photon pairs, we have a beam splitter, we have a delay, and we have our detectors. But one of the two mirrors here is replaced by a sample. So some sample that may have multiple surfaces, internal surfaces. It could be biological, it could be something like tissue or something. Okay, so in the original proposal, the two things that stood out as advantages over the classical systems is an enhancement by a factor of 2 in resolution for the same bandwidth as a comparable classical system, and even order dispersion cancellation. So what this means is that if one of the photons goes through some dispersive medium, it will shift the Hong-Mandel dip, but it will not increase its width. And this means that the resolution is maintained. It doesn't get affected at all. So let's think about the simplest possible sample. So just having two layers. So I have a reflectivity from one layer and from the second layer. So if we run the Hong-Mandel experiment, we will now have two dips, one for each of the two interfaces. But we will also have this thing in the middle. So this thing in the middle is a cross-interference term. One dip has to do with the signal photon reflecting from one surface. The other dip has to do with a single photon reflecting from the other surface. And this thing can be thought of as the result of the signal photon being reflected partially from each of the two surfaces. So the point is that these two dips can be used to establish the positions of the two surfaces, and this thing in the middle can be a problem, because as I will show, it can be either a peak or a dip, and it's easy to confuse it with a third possible layer, which is non-existent, for example, or if the two dips are very close to each other, they could overlap with the intermediate structure, and this will be a problem. So we have a model based on this is the joint amplitude of the two photon states, and basically this is just a simple Gaussian model which has a Gaussian dependence on the diagonal and the anti-diagonal. So it looks like kind of like this. This is in frequency, and this is the same thing in time. So this is a Fourier transform joint spectrum. Now, if we do the calculation of the fundamental interference, we get this. So we get 3 different terms plus the background, and 2 of them are interference dips, and the third one is what I'll call the intermediate structure. These V0 and V1 are the visibilities, which have to do with the reflectivities of the 2 surfaces, and V middle has to do with this effect that we want to suppress. So this is a cosine of this omega 0, which is the pump frequency, and capital T is the temporal separation between the 2 surfaces. So it's the time it takes a photon to cross the sample. And so this means that it can be either positive or negative, and it can be either a peak or a dip. So this is our experiment. We have a titanium sapphire laser, and we downconvert the PPLN crystal to 1.55 microns. By the way, this, as far as I know, was the first QOCT demonstration in the telecom band. This is good because infrared photons will have a greater penetration depth. Also, we made an effort to make it all fiber, except that the photon needs to come out to interact with the sample and then come back into the fiber. And on the other side, we also have a free space delay. So the 2 photons are, one is sent through a circulator, which helps us to, the photon comes through one arm, comes out through the second arm, to the sample, comes back through the same arm, and comes back out through the third arm, then to a beam splitter. And we have the other photon, which simply goes through a free space delay, and we have a beam splitter where the interference takes place, and we have the 2 avalanche photodiodes. So this is some of our data, and what we did is we did the same experiment 3 times by changing the laser. Well, actually we have 2 lasers, one is picosecond and one is femtosecond. But also one of the 2 lasers can be run in CW mode. So it's like having 3 lasers, and we did experiment 3 times. And as you can see, if we have a CW laser, we have the 2 dips and the intermediate structure. If we go to a picosecond pump, the structure in the middle kind of is somewhat diluted. And if we go to the femtosecond pump, it's altogether suppressed. So we showed basically that we have, if this condition is fulfilled, which this omega d is the antidiagonal bandwidth, and T is the, as I said, the temporal width of the sample. So if and this is related to the pump bandwidth. So the pump bandwidth is greater than 2 over the temporal width of the sample, then we can completely suppress this middle structure. So that was a nice result. And also, if we do the same experiment with a CW laser, but we tune the laser, we can see that we can go from a peak to a dip to nothing. And this is the same thing with many more points, and you can see that we have a nice cosine dependence. Okay, so now I'll switch to the second experiment. And so the point of this second experiment is that in real life, of course, samples are 3-dimensional, so we want to acquire the full transverse information for each axial position. So as we vary the delay, we need to acquire the full transverse picture. So we use an ICCD camera that is operated in coincidence with an APD. So the basic apparatus is very much the same. We have fundamental interference, but one of the 2 arms coming out, instead of using an APD, we use an ICCD camera, which allows us to do coincidence counting. And just a comment, because this camera has a very large insertion loss, we need to send this photon through a very long free space delay to compensate for this insertion delay. So what do? We have a sample which has 2 surfaces as before. We have some thin copper deposition applied on both surfaces, and this deposition is designed so that we have a reflectivity of 0.45 from the first surface and 0.8 from the second surface. And also we have like two frames. One frame is left empty, and the second frame we laser imprint. We basically through laser damage we create a letter psi, and what we do is we remove the copper within that letter psi. So you have two frames, and so we repeat the same kind of experiment that I showed before, but with spatially resolved coincidence counting, and with this sample. So first, this is what a single layer looks like. So this is just going back to the regular Hangul-Mandel with just a single mirror instead of a sample. So we have two cases, unfiltered and filtered. So this is just to show that if we restrict the bandwidth of the photon pairs, we get actually these are the other way around. This is the filtered. This is the unfiltered. The point is that if we filter it, the visibility pretty much reaches 100% or 95% or something, but the width of the dip is considerably larger. If we go to the case where there's no filtering, then we reduce the visibility, unfortunately, but we improve the resolution. Basically, the width of our Hangul-Mandel gives us the resolution. Okay, so now we go to two layers. And as I've already discussed, we have a dip for each of the two surfaces, and we have this additional intermediate structure. And so here, what we've done is now I have placed the sample, and what we can see here is that there is a little bit of an effect in going from the empty frame to the letter psi. But of course, we don't know anything except that there's something that is different. So this is these are the results with the spatial resolution. And what we see here is, so this is the transverse, these are the spatially resolved coincidence counts at 6 different locations. So number 1 is like left flank of the first dip, just before the first dip. The second one is right in the middle of the first dip. The third one is right flank of the first dip, and so on. And these 3 for the second dip. So what we see here is that when the visibility is maximized at each of the 2 dips, we get the letter psi. In one case, it's kind of the counts are kind of higher than the background, and in the other one, it's the other way around. So in order to explain this, these results are going to appear shortly in this new OSA Journal of Photonics Research, which apparently is some collaboration between OSA and Chinese people. Anyway, yeah. So anyway, here's a schematic of our sample. So we have the regions which are labeled intact. There's no laser damage, and then there's the damaged region. So the thickness of copper is of course reduced, and the reflectivity presumably is decreased in these areas. So we define the visibility contrasts, which means the visibility within the laser damaged region as compared to the intact region. And just doing the same calculations based on the model that I showed you before, it's easy to show that as we reduce the reflectivity in the damaged region from 0.45, which is a nominal value for the intact area, we get a reduction in the visibility contrast. Whereas if we look at so this is for the first dip. For the second dip, it goes the other way around. Here we have numbers which are greater than 1, whereas here we have numbers that are lower than 1. So this explains why we get this enhancement or depression of the letter psi. Okay, so now I'll go to third topic, which has to do with amplitude transfer in the FKDC process. So this is going back, this is an old paper, but just to show some of the basic ideas. So this is the SPDC cone. So if I go back to one of the first slides, we had this very well-known cone, right? So this is what that cone looks like in transverse momentum space. So if we fix the position of one detector on one side, we can ask ourselves, what does the other photon look like? Like if you could take a photograph of that photon, what would it look like? So here's a plot at different locations of what this other photon looks like for a specific source, and in two different cases. In one case, it's a pump which is collimated. It's not particularly focused. In this case, it's the same crystal, the same everything, except that our pump is highly focused. So what I'm showing here is, well, I forgot to include an equation here, but what this shape of the other photon, 5 minutes, okay, is called the conditional angular spectrum. This conditional angular spectrum is given by the product of two different functions, which are the angular spectrum of the pump times this other factor which has to do with phase matching and so on. So in going from here to here, the only thing that is different is that the angular spectrum of the pump has grown because we are focusing. And now this other function will have an effect, whereas here this function is so small that it doesn't have any effect on the overall function. Over here, there is an appreciable effect, so we get this sort of azimuthal distinguishability. So anyway, I'll try to go a little bit faster. So we have done some experiments over the years with Bessel beams used as a pump. Here I show some measurements of the angular spectrum of a Bessel Gauss pump for different what we call KT parameter, which is the radius of this cone. And this is what we obtained for the STDC. The STDC cone will turn into two different cones. So we can see an external cone and an internal cone. This is sort of well known from a few years ago, and this is an experiment from 3 years ago where we compared the paraxial with a non-paraxial case. So we have a Bessel beam, which is kind of a small cone. This is a much larger cone. And what we show here is the same kind of data as was indicated here. So we go around the cone and we ask ourselves, what does the other photon look like? So here we have these small donuts that basically are identical to the structure of the pump. So the pump is just inherited to our single photons, and it doesn't matter where we are on the cone, we always have the same picture. Over here, we have this very different case where we have the azimuthal distinguishability, and we have a strong dependence on the position around the cone. Now, to show you the latest results. So we want to show something very simple. If we just take so by the way, we use an axicon to make these Bessel beams. And in order to have a way to engineer our photon pairs, which is particularly simple and just easy to do in the lab, what we can do is we can introduce some kind of obstruction, physical obstruction on the Fourier plane, on the transverse wave vector plane. So in this case, we have the intact angular spectrum of our pump, and now we just add an obstruction, and now we get half of this angular spectrum. Here's what the actual beam looks like, and in the intact case, and what it looks like once it's obstructed. And what we can see is that so what we can do is we take this obstruction and we can rotate it around, right? So here there's 4 different cases of 4 different angles for this for the orientation of our obstruction, and we can see that we can select either the external cone or the internal cone for the sort of upper half or lower half, or if we have some other orientations, we get kind of a portion of each of the 2 cones. So we get this kind of curious spiral case. And this is just a lot of these put together in a nice movie. Here's some other orientations that are sort of diagonal. Okay, so if I have time, just like 2 minutes, I'll just really quickly talk about OAM conservation. So OAM entanglement has been used for some time. This is the first paper from Seidlinger group from 2001. And basically, in some cases, not always, OAM is conserved, so that if one photon has, for example, a topological charge L on one side, then on the other side we're going to have minus L. So here's a two-photon state which shows this, so 1, minus 1, minus 1, 1, they all add up to 0, assuming that the pump has no OAM. So we did a nice experiment, or I think it's a nice experiment, where we take our photon pairs, and on one side we use a liquid crystal display to sort of imprint a phase with the negative. So if we have here, for example, topological charge of L, we undo this with the opposite phase, so we have minus L, so that we end up having a Gaussian beam which will couple well into a single mode fiber. And we can just change the value of L here, and we can project one of the photons to any L value. And on the other side, we detect our other photon in coincidence, and we directly visualize these OAM conservations. We directly see how the other photon responds, the angular spectrum of the other photon responds. So just quickly, these are the phase masks used for different values of L. This is just a verification that in going in reverse, so we illuminate the screen, and then we can create a beam that has an angular spectrum which as expected grows with the value of L. And from this we can just select different values of L on one side. So we project that photon, and we see that the other photon will look different according to all of the different values of L. So this is just this was not anything unexpected, but it's just nice to see in a very visual way these OAM correlations, OAM conservation. And also by integrating over all of the pixels here, we can get the OAM spectrum. So it's maximum in the center, and then it decays more or less symmetrically. And well, okay, I think I'll stop here. Oh, just 30 seconds, if I may. Coming out of the system, one of the things that we can do is directly verify that we have OAM. So if we do diffraction through a triangle and look at the far field diffraction pattern, for example, here for the either the -1 or the 1 values of L, we get this well-known triangular pattern with 3 lobes, and this is an indication that we have a topological charge of 1. But also we can distinguish between -1 and 1, because there's a rotation, a relative rotation between these two patterns. And if we go to the L to -2 or 2, then we get 6 different lobes. And likewise, we can distinguish between -2 and 2. So anyway, I'll stop now.
Thank you. We only have time for 2 questions. Any question? Okay, we have one there. And then another one. No?
I think there were no questions.
Yeah, if I understand correctly, so in this nonlinearity, when you use these tapered fibers as a source, you rely on the nonlinearity of the glass that it's
That's right.
The regular fiber. I mean, have you?
Well, it depends. So we have used these tapers in 3 different ways. In one experiment, we created photon pairs in the taper through a Chi3 process, spontaneous for remixing, and then the radius of the taper can help you to engineer the photon pairs. In particular, you can tune them. But then we also use them. We've tried to use them to make photon triplets, and again, we are relying on the Chi3 nonlinearity. But also, we are using them to couple light into macro resonators.
So my question: are these regular fibers, or do you Or have?
So we have made tapers from, for example, bow tie birefringent fiber, but mostly we use just SNF28, which is the cheap fiber.
It's possible to make, I don't know, to get a fiber made from what usually nonlinear crystals are made of? Or
no, I don't think so. I haven't heard of that.
okay.
We have time for one more question. Well, if there are no more questions, we thank all the speakers for these sessions.